So we already know that the strength of an acid or base is determined by the extent to which it ionizes, which means that we can express this in terms of equilibrium constants. If we're talking about the ionization of an acid, we call it a Ka. If we're talking about the ionization of a weak base, we call it a Kb. We really only use Ka and Kb for weak acids and bases, because they're the only ones that are going to have an equilibrium setup. A strong acid or base is going to 100% ionize, which means there's no reverse reaction. Your Ka would be so large, so incredibly product favored, that it's not really a useful quantity at that point. Setting up what our expression for Ka looks like, though, we've got our acid dissolving in water, and then our products here is the H plus and whatever the rest of the acid is. Our reactants are the whole acid and the water that we're dissolving it into, but since water molecules don't appear in an equilibrium constant, these are the only things that we would need to plug into our equilibrium expression. So this is our equilibrium expression for an acid. Hold on, there we go. Now, how do you know if we're dealing with a strong versus a weak acid just on site? The good news is there's not that many strong acids. So these are the 7, and you just have to know them. They are on your things you just have to memorize list. If you see any of these 7, we can assume 100% ionization. Any other acid, we would assume it is a weak acid, and therefore we're going to have to watch for a Ka value. But again, for our weak acids, only partially ionizing in water, meaning at equilibrium, we are going to have mostly the whole acid molecule and a very small percentage of these products that we see right here. Here's the graphical version of that. One way to measure the strength of an acid besides the Ka value is the percent ionization. And as this implies, our percent ionization is how much of the ionized acid we have divided by the initial concentration of the acid. So the stronger that acid would be, the greater the percent ionization. And the stronger that, the higher the percent dissociation, the stronger the acid is going to be. Because the higher the percent ionization, the more of these two things you have, which would increase the value of your Ka. So as an example, here's our generic weak acid with formula Ha. If I've got a concentration of 0.2 molar and it's a little over 1% dissociated, how could we calculate the Ka for this acid? Since we're told what percentage of our original concentration dissociates, we start off with our original concentration and then take 1.2% of that. That tells us what the concentration of the H plus is going to be. If we know the concentration of that H plus, we also know the concentration of the other half of the acid because they are the same thing. We were given our original concentration to begin with, and then we can plug all of those numbers into the Ka expression to solve for our actual value of Ka, which in this case would be 3.05 times 10 to the minus fifth. All right, pause the video here and see if you can go the other way. Given a Ka value, given a pH, think about what pH tells you. Pause the video and give this a try. Did you pause it? All right. So think about what information you've got. If you're given a pH, that's really telling you what the H plus concentration is. Inverse log of negative pH gives you your H plus concentration. We know that the H plus and the other half of the acid have to be the same thing. Then we can calculate what that H whole acid molecule concentration was using the Ka value. You've got the Ka, you've got the H plus and the other half of the acid. All you needed to solve for then was the original concentration of the acid. If you know what the original concentration of the acid is, now we can find the percent dissociation, because we've got the amount of H plus that we have divided by the whole original concentration. This was the thing you had to work a little bit harder for, and that gives you your percentage dissociation. All right, try this one. Pause video, give it a shot. Okay, if you're given the Ka value, you know that that Ka equals the H plus times the other half of the acid over the entire acid concentration. We were given the entire acid concentration. We weren't given either of these two things, but we know that they had to be equal to each other. So I can replace that with x squared. Solve for x, that gives you your H plus concentration. And then negative log of your H plus concentration gives you your pH, which, if we've done it right, you should get 5.18. Now with di or triprotic acids, we said before that only one hydrogen tends to come off at a time. Every H plus that comes off has a different Ka associated with it. Here's an example with phosphoric acid. The first Ka is pretty high, 7.1 times 10 to the negative third. Notice as you go to the second and then the third, we jump to times 10 to the negative 8th, times 10 to the negative 13th. So if we're thinking significant figure-wise, really that first hydrogen coming off is going to be the only significant contributor of H plus ions into the solution. The second and third are going to be relatively so much smaller. We generally, in a multi-step problem, would ignore them. They're not going to give us enough H plus to make a noticeable difference in that pH. With bases, we've got really the same idea going on. We'll just call it a Kb rather than a Ka. For strong bases, we could recognize those as the soluble hydroxides, things like sodium hydroxide. It'll dissolve in water, 100% of them come apart. Tells you how much hydroxide you have. But with weak bases, these are the things that will only partially ionize in water. The only one that you'd have to recognize on site, like I said the other day, was ammonia. Otherwise, you would be given an equation like this one here in order to recognize where the hydrogen went. The way you would set up your equilibrium constant, though, is pretty much the same as with Ka. The base reacting with water here gives you the conjugate acid, so our original base with the H plus attached to it, and hydroxide. So like any equilibrium constant, our products on top, reactants on the bottom, the pure water, which that should say liquid, not aqueous, your pure water not listed in the equilibrium constant. So you'll notice that your Kb expression looks a lot like your Ka expression. There's the two ionized pieces of your base on top, and then the whole non-ionized base on the bottom. And we'd handle math problems with it the same way you would Ka. So take a moment, pause the video, try this one. Really do pause it. If you got a pH of 10.2 here, good job. Basically, you're taking your Kb value. That has to be equal to your OH minus and your conjugate acid. Your original base should be on the bottom. You were given the concentration of your original base. You don't know these, but you know they're equal to each other. So just like with your Ka problem, you've got x squared over the concentration of your original base. What makes this one tricky is that when you solve for x, that gives you an OH minus concentration. So if you take negative log of this, that gives you a POH, and then you'd have to subtract from 14 to get that into a pH. Only tricky thing you got to watch for is if you're dealing with Kbs, it is a hydroxide concentration that you get directly. Then you just got to watch for getting that into a Ka. Oops, there we go. So if we look at relative acid and base strength, we know that acids turn into conjugate bases, bases turn into conjugate acids. So the stronger your original acid, the weaker its corresponding conjugate base would be. And the stronger an original base, the weaker its corresponding conjugate acid would be. That way, if we put weak acids and weak bases together, we can start to see which direction that equilibrium would be primarily driven in. Remember that in an equilibrium situation, we'd have to look for which way is going to be most favored. The stronger base here is going to control the direction. If I put, for example, a weak acid in water, acid being the acid, water being the base, whichever, you have a competition for the H plus going on here between the base and the conjugate base. If water is better at grabbing onto that hydrogen than the conjugate base is, then it's going to take the hydrogen and that moves the equilibrium to the right. If the A minus is the stronger base, it's going to be the one to take the hydrogen and that moves the equilibrium to the left. So we can tell which way our equilibrium is going to go based on looking at these relative strengths of the bases. We also talked about water, and that in any water solution you've got H plus and OH minus both there due to our equilibrium constant for water. And we had to specify that temperature was 1 times 10 to the minus 14. But like all equilibrium constants, that Kw is dependent on temperature, which means that the pH of pure water could be something other than 7, which is kind of trippy. For example, at 10 degrees Celsius, the equilibrium constant for water is a little bit off. Okay, instead of 1 times 10 to the minus 14, if we drop the temperature, our Kw drops to 3.1 times 10 to the minus 15. So if we calculate the pH of water at this point, we'd have to plug that Kw in. H plus and OH minus, we don't know what they are, but we know they're equal to each other. So I can replace that with x squared. Solve for x, that gives me an H plus concentration. Negative log gives me a pH. At 10 degrees Celsius, the pH of water becomes 7.25. So the question then, is water basic at 10 degrees because my pH is above 7? And the answer is no. Because your H plus and your OH minus are the same, that's the definition of neutral. So the trippy part is pH of 7 is only neutral at 25 Celsius. If you change the temperature, you actually have to change the definition of what's neutral. So in order to not have to deal with this confusion, questions will always specify 25 degrees Celsius. If it doesn't specify, you can assume that. The only time it wouldn't be is if the whole point of the question is something like what you see here. Could you show why the pH changes at different temperatures? Otherwise, all other pH math, unless that's the point of the problem, all other pH math we can go ahead and assume 25 degrees Celsius and avoid that nonsense. All right, so because this equilibrium constant for water relates H plus and OH minus, it also relates the Ka value for an acid and the Kb of its conjugate base, or the Kb of an original base and the Ka of its conjugate acid. They will be related to each other. So if I have this weak acid, it's lactic acid, given a Ka value, let's see if we can write the net ionic equation for the reaction between the conjugate base for this and water, set up the Kb, and then calculate the pH of that solution. Kind of put this all together. So first, look at that weak acid here and write the net ionic equation for the reaction between its conjugate base and water. Oh, I didn't animate this. Oh. My conjugate base would be the C3H5O3 minus. Put that in water, I would get the original acid and OH minus. So the water would be acting as the acid here. Hydrogen would have to jump from the water to this weak base, giving me a conjugate acid and a conjugate base here. The Kb for this reaction as written is provided to you. So now I've got a value for this Kb, that goes in this spot. There it is. My concentration of the original solution was provided to me, goes here. I don't know what either of these two are, but I know they have to be equal to each other. That's what allows me to plug in like this. Solving for x gives me the OH minus concentration. So be careful when you're dealing with Kb's, it's an OH minus concentration that you get. And then negative log of your OH minus concentration gives you a POH. Subtract from 14, gives you a pH.